Hello everyone. So let's start solving the last set of 5 organic questions from the JAM 2018 question paper, right? So the first question says, among the following hydrocarbons, how many of them would give rise to 3 groups of proton NMR peaks with 2:2:3 integration ratio? So basically first it says it should have 3 groups of protons. That means 3 sets of protons are required. So 3 kinds of proton which are in chemically different environment. Apart from that, the ratio should be 2:2:3. So this peak number, the integration ratio, the integration shows the number of similar peaks, not similar, identical peaks. And because it's in ratio, numbers can vary, but ratio will give certain idea. So let's look at the questions. So first question is methane, ethane, propane, butane, pentane, hexane, right? So let's solve here. So hexane is there. So now you see this terminal CH3 and this terminal CH3 are exactly in the same identical environment, because if I move from here I see a CH2, 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 and then it comes same. Now similarly these two CH2s which I have marked as B, these two hydrogens are these two sets of hydrogens are identical because they both have same environment. Similarly this C have same environment. So now 3 plus 3, how many protons? That is 6. So we write here 6. Then here how many are there for the B? 2 plus 2, because CH2 is there, CH2 is there. 2 plus 2, 4, and again C is also 2 plus 2, 4. So 6 is to 4 is to 4. So that comes to 3 is to 2 is to 2. But what we need is, yeah, we need 3 is to 2 is to 2. So this is this molecule does definitely have the had 3 sets of hydrogen in the ratio 3 is to 2 is to 2. So you appreciate this point, right? Because it is 6 is to 4 is to 4. So we divide all of them by 2. So 2 3s are 6, 2 2s are 4, 2 2s are 4. So the ratio is 3 is to 2 is to 2. Moving on to the next molecule. So next molecule is methane, ethane, propane, butane, pentane. Again this A and A, these are identical, these two are identical, and this third one remains alone. Okay. So now how many protons are there? So this is 6. So 6 is to 4 is to 2. So it comes to ratio, again we divide by 2. So we get 3 is to 2 is to 1. And the final one, let's look. So this benzene ring have identical substituents on the para position to each other, right? Here and here at position 1 and 4 we have identical, that is ethyl. So therefore all the 4 hydrogens on the benzene ring are same. So that I have put as C, that is 4. So I have put 4 here, and then again same, this C2CH3s are same. So the 3 plus 3 is 6, and again 2 plus 2 is 4. So 6 is to 4 is to 4, that comes to 3 is to 2 is to 2. So this is what is needed. So molecule 1 and molecule 3 has 3 sets of proton in the ratio 3 is to 2 is to 2. So the answer is 2. Moving on to the next question. The question says the number of stereoisomers possible for the following compound is. So we have to see how many number of chiral centers are there. Chiral centers means on the carbon all the 4 substituents are different. So this is one chiral center, because here one of them is one of the substituent is hydrogen, one of the substituent is phenyl group, one of the substituent is OH, and then rest is this whole part. Similarly this also has 4. So the basic formula is 2 to the power n. So 2 to the power 2, that equals to 4. Therefore we expect this to have 4 stereoisomers. But the problem is sometimes a pair of them which appears to be stereoisomers, that means they look like enantiomers but they are identical, because if there is a plane of symmetry in that stereoisomer, then the enantiomer will be one and the same. So let's understand what is enantiomer, what is diastereomer. I will just show you this. So it has 2 chiral carbons. So first I have put both the OH on the right side. So both the OH comes on the left side. Then we have both the OH on the left side. So both the H on the right side. Then top OH on the left, down OH on the right. then top OH on the right and down OH on the left. These are the 4 possibilities. You can think for yourself, there is no more possibility, right? Now what is enantiomer? Enantiomer is pair of stereoisomers which are mirror images to each other but not superimposable. So let us look at C and D. Let us look at C and D. So these two are mirror images. Why? When you look at the mirror, what do you see first? You see your nose first, because nose is projecting out. So nose comes from there also first. Similarly, this hydrogen is front, so this side also hydrogen. That OH is behind, so this side also OH is behind. And you can see here this OH and that H and pH. Now the thing is, this is what is called as Fisher projection formula. So in Fisher projection formula, the vertical substituents are away from the viewer. So this pH actually is behind the screen, and similarly this pH is also behind the screen, and the substituents which are in horizontal position are towards the viewer. So because you are the viewer, you are watching from the screen, so that means this OH and H is coming towards you. Similarly, this H and this OH are coming towards you. So now we cannot rotate the molecule like that so that pH comes front, because when you do that, then we cannot check the superimposability, because now if we turn it like that, then what is pH is away from the viewer, then pH comes towards the viewer, then I cannot check the superimposability on this. Right now I want to look if they are one and the same. If they are one and the same, then they should be superimposable on each other, right? Superimposable means they 3-dimensionally they should exactly fit on each other. So if I have to fix 3-dimensionally, I cannot rotate it like that, means outside the screen 180 degrees. Then pH which is away from the viewer will come towards the viewer, and then so 3-dimension that whole structure lost. So let us look first. So if I put this molecule on top of this, we will see that these two pH are superimposing, but this H is coming on this OH and this OH is coming on this H. That means they are not superimposing on each other, right? But we have the freedom of rotating this molecule on the plane of the paper 180 degrees. So I can rotate it something like this and then also check the superimposability. So when I do this, what happens is this pH, down pH goes up and this up pH comes down. So let me draw it for you. So the down pH has gone up and the up pH has come down, right? And what else has happened? Now this has gone up and this side, so you can imagine 180 degrees like this. So this OH has come to the right side and H has come to the left side. Think about it. Once you're clear, then only move forward, please. Similarly, this also has rotated 180 degrees. So this OH has come to the left side and H on the right side, and H on the right side. Fine. Now look, we are getting exactly same thing. That means these two are not superimposable on each other. So these two are pair of enantiomers. Okay. Now there is another concept what is called as diastereomers. So diastereomers means pair of stereoisomers which are neither superimposable on each other nor mirror image to each other. So let us look at this. Is this mirror image? So this H is coming here, so H should have been here. That means this part is not mirror image. This part is mirror image. You see, this H is coming this side, this H is this side, this part is this side. But you see that this top part, no, this top part is superimposable on this. This pH fits on this OH fits on this, and this H fits on this. So the half of the molecule is superimposable and half of the molecule is mirror image. So that means overall what happens? The molecule is neither superimposable nor mirror image, because one half, this half is mirror image, whereas this half is superimposable. So overall neither superimposable nor mirror image. So these are pair of enantiomers. Similarly, if you look, B and D also are enantiomers, right? Now the problem with A and B are identical. How we'll know that is? Even without drawing A and B, we should be able to tell that there are not a pair of enantiomer not possible, because the molecule has plane of symmetry. Let us see this. If I cut this molecule from here, It's a plane, just like a paper I cut it. So I should get exactly same thing. So you see, when I move here I find OH, when I move here I find OH, when I move here I find H, if I move here I find H. I move a distance of 2 carbons, I find pH, move to distance of 2 carbons, I find pH. That means we are getting exactly identical halves. So it has a plane of symmetry. That means if I draw the enantiomer, what we do, that one 2OH here and this 2OH here, actually if we see that, you will find out that they both, though it appears like mirror image at the beginning, you see here OH is coming this side, OH is coming this side, OH is coming this side, OH coming this side, but actually they are not mirror images, they are identical. How? I said initially we have the freedom to rotate it 180 degrees in the plane of paper. So I am rotating it like this. So what happens? The down pH goes up and the bottom and the top pH comes down. And what else happens? Now this is going like that. So this H is coming up but on the left side, and OH is going on the right side. Same thing happens for the down chiral carbon, and what do we get is again same OH and H, OH and H. So now it's very clear that these two are superimposable on each other. These two are superimposable on each other, and thus it's very clear that they are one and the same, and therefore the number of stereoisomer reduces, because now both are same. So I cannot write A and B, I have to just write A and then we C and D. So the number of stereoisomers are 3. Moving on to the next question. The next question says the number of hydrogen bonds present in guanine and cytosine. So you know in DNA there is ATGC. ATGC. Just remember, first one is double bond, second one is triple bond. That's how they pair up. GC, right? So between A and T, that is adenine and thymine, between adenine and thymine there are 2 hydrogen bondings, and between guanine and cytosine there are 3 hydrogen bondings. If you want, you should see the structure. So G and C, guanine and cytosine, there are 3 hydrogen bonding possible, and adenine and guanine there are 2 hydrogen bonding possible. Next question. Next question says the elemental analysis of organic compound containing carbon, hydrogen and oxygen gives percentage composition of 39.9%, 6.7% of hydrogen. So carbon is almost 40% and hydrogen is 6.7%, and the molecular weight is 140. It is asking the number of carbon atoms present in the molecule. So these questions are very simple. Don't solve as percentage, take them as mass, and it becomes very easy. So it says given percentage of carbon is 39.9. That means out of 100, 39.9 is carbon, hydrogen is 6.7. So how much is oxygen? So 100 minus this plus this, so that is 53.4%. So let's find out percentage mass of the elements, because just by seeing this percent composition, what they give here is mass percentage. By mass we cannot make out anything. What we need is what is the ratio of the moles, right? So what we will do is, let's imagine we had initially 100 grams of compound, because we talk in terms of percent, so 100. So 100 grams. So how much mass of carbon? Because 39.9%, that means if 100 grams is there, mass of carbon is 39.9 grams, mass of hydrogen is 6.7 gram, and mass of oxygen is 53.4 grams. So now if we very clearly, if we have mass, we can easily find out moles, because number of moles is equal to mass by molar mass. So what is mass? 39.9 grams. What is molar mass of carbon? 12 grams per mole. So that comes to 3 moles. Number of hydrogens, again mass by molar mass. So molar mass of hydrogen is 1, it's coming to 6 moles, and moles of oxygen, again mass by molar mass, that comes to 3. So empirical formula is C3H6O3. So let's find out what's the empirical mass. So empirical mass is coming to 90 grams, right? But here clearly it says the molecular mass is 180. So that means this is the empirical formula. We have to multiply with some whole number so that we get the real molecule. So 90, but the original is 180. So 180 by 90, this gives you 2. That means X value is 2. So the molecule formula is C6H12O6. So the number of carbon atoms are 6 in the molecule. Next question is, the number of compounds having S configuration among the following is. So we are having these molecules and it says S configuration. So we know R and S are absolute configuration. So before giving the configuration, few things we have to know. First we have to give priority to the substituent. Priority is given according to the atomic mass. Fine. This happens when you have a plane of symmetry. Sometimes you have axis of symmetry like this molecule. Then we have to follow different procedure, we will find out. So first is, how do we give priority to the substituent? So we give priority according to the atomic mass. We go bond by bond and look at the atom with the highest atomic mass. So wherever we find a difference, that means an atom we find which has one substituent which we find which has higher atomic mass atom, we stop there and we give the CIP rule configuration. And then if we have axis of plane of symmetry, plane of asymmetry, not symmetry, sorry, plane of asymmetry, that means should not be symmetrical this molecule. And then the hydrogen, the lowest priority substituent has to be away from the viewer. Then only we can find out the absolute configuration. So here very clearly you can see this hydrogen is away from the viewer. So whatever we get, we will have to write it. Here we see hydrogen is towards the viewer. So whatever we will get, we will write opposite of whatever we are getting, right? The problem is, if hydrogen is in plane, then you have to rotate the molecule in such a way so that the lowest priority, see we are saying hydrogen here very clearly because we know hydrogen has lowest atomic mass in whole periodic table, atomic mass is 1. So if hydrogen is in the plane, then you rotate in such a way so that hydrogen goes away from the viewer, right? And this is the Fisher configuration. So in Fisher, I told you previously also, just a last question, the horizontal substituents, sorry, the vertical substituents are away from the viewer and the horizontal are towards the viewer. So here horizontal is towards the viewer, this hydrogen is towards the viewer. So whatever we are getting, we will write opposite of it because we wanted the hydrogen to be in vertical line so that it is away from the viewer. But here it is towards the viewer and you are the viewer. So what we do is basically we prioritize the substituent, and after prioritizing them, we look at the spatial arrangement of the first 3 substituents 1, 2 and 3. If the first 3 substituents are arranged clockwise direction, then it is R. If it is arranged anti-clockwise direction, then it is S. But with the rule that lowest priority is away from the viewer. So let's look at this molecule. So here CIP rule will go. So this is the chiral carbon. We have to look at all the 4 different substituents of this chiral carbon. So first substituent is bromine. So bromine is 1, right, because bromine has more atomic mass than carbon, carbon and hydrogen. So fourth substituent also is very clear because hydrogen has lowest atomic mass. Now the problem comes here because first substituent here it is carbon, here also it is carbon. So we cannot differentiate. So we go to the second bond. Second bond is what? 2 hydrogens and 1 carbon. Here it is 3 hydrogens. So here 1 carbon is there. Carbon has more atomic mass than hydrogen. So this gets second preference and this one gets third preference. Okay. So now what did I say? Hydrogen should have been away from the viewer and here it is away from the viewer. So whatever we are getting the spatial arrangement, that's what we will write. So now look here what happens. The 1, 2 is here behind and 3 is here, right? So the rotation is going like that. This is anti-clockwise, you know, clock rotates like that, like that, like that, like that. So this is called as clockwise rotation. This is called as anti-clockwise rotation. So if it is anti-clockwise rotation, it is S, and because H is away from the viewer, straight away will tell configuration is S. Here let us give the priority according to CIP rule. So, first again oxygen gets first priority, this gets second priority, this gets third priority, and this gets fourth priority, right. And now the hydrogen is towards the viewer. So, that is the problem, we wanted hydrogen to be away from the viewer. So, you can do some operations so that hydrogen goes away from the viewer, but you need not do all those things. If hydrogen towards the viewer, just see how is it rotating. If it is rotating clockwise, it should have been R, but it will be S. If it is going anti-clockwise, it should have been S, but it will be R, because the lowest priority is towards the viewer, though it should have been away from the viewer. So, here first priority, so let us look the spatial arrangement of 1, 2 and 3. So, it is 1, 2 and 3, it is going again S, see anti-clockwise. So, looks like S, but it will be R, looks like S, but it will be R because of the rule which we said, because hydrogen is towards the viewer. So, this is R. Here what happens? Here you have to start looking at the molecule from one direction. So, you have to clearly define the point of view. So, let me start looking from point of view here. Okay. So, you are looking from your mobile or laptop, you are looking. So, you are looking from front of the screen. So, basically what you are doing is you are turning it like that, so that this part is towards you, and then we have to give priority, and priority will be giving these two separate, because I am looking from this side. So, first 1 and 2, and then we will give these two separate, and here again we are comparing only these two, but we will write them 3 and 4. I hope I am making sense. So, once again I will tell you what I am doing. I am pulling this molecule front of you. So, what I am seeing is here, see, H is coming out of the screen and this CH3 is coming out of the screen. So, these two will get the first priority and whole thing is gone behind. So, this is gone behind. So, behind the screen your H is in the right direction and behind the screen your CH3 is on the left direction, right. So, what do we do is, let us look at them, So, between CH3 and H, of course, CH3 will get first priority and hydrogen gets second priority, and here 1, 2 is done. Now, here 3 and 4 we have to write. So, CH3 gets more priority, hydrogen gets less priority. So, it is 4. Now, we have brought it here. So, we will write it like this. This side is left is 1 and 2, right. Sorry. Oh, sorry. When I am pulling it front, I did mistake. I am so sorry. This hydrogen is coming on the top and CH3 is coming below, but is coming out of the board. Please remember this. It is coming out of the board. So, out of your screen. So, how we will be writing 1 and 2 is 1 will be top, 1 will be, sorry, 1 is CH3 and hydrogen is 2. So, 1 is down and 2 is on top. Please remember, we are giving priority according to how I am viewing it. I am viewing it from this side. So, from this side what I am seeing? I am seeing hydrogen on top, CH3 on down, and I am pulling it front, so that I am seeing from the screen hydrogen is coming out of the screen, but hydrogen is on top, and CH3 is coming out of the screen, but CH3 is coming down, and therefore, I am writing CH3 the first priority 1 down and second priority 2 up. And because I have rotated it like that, so that they come out, what we see is this whole thing has gone this side. So, hydrogen is coming behind the screen, but on the right side, and CH3 is behind the screen, but on the left side. So, 3 is coming here, 3 is coming here, and 4 is coming on the right side. I hope I did not confuse you much. Initially got a bit confused, but that is what it is. And so, now let us look at the spatial arrangement of 1, 2 and 3. So, 1, 2 and 3 is coming like this, okay. 1, 2 and 3 is coming like S. So, it is S priority. So, this is S priority, fine. Moving on to the next question. Next question is very simple. Hydrogen is towards the viewer. So, we will give priority and then after that whatever we are getting, if it is going clockwise it should come R, but we will write S. If it is coming anti-clockwise, so it should be S, but we will be writing R because the lowest priority hydrogen is toward the viewer. So the first, all of them are carbon, one of them is hydrogen. So hydrogen has lowest atomic mass, so we can straight away give fourth priority to hydrogen. Now we have to go step by step. So this is carbon, this is carbon, this is carbon. Next what? This has 3 hydrogens. This has triple bond nitrogen. Cn is triple bond nitrogen. So that is considered as carbon is attached to 3 nitrogen atoms. That's what we do in absolute configuration according to CIP rule. So here carbon attached to 3 nitrogens, whereas here carbon attached to 1 nitrogen and 2 hydrogens. So of course this gets first preference, this gets second preference, and this one gets third preference. Okay. Now we have to look at the spatial arrangement of 1, 2 and 3. So 1, 2 and 3 is coming clockwise, right? So it looks like it is clock moves like this. So it looks like R, but it will be S because hydrogen is towards the viewer. So this will be S. This will be S. Now again here hydrogen, the lowest priority is towards the viewer. So what I will get, will write opposite of this. So this gets fourth preference. Now CH3 will get last preference. 1, 2 and 3 it should get third preference because carbon attached to 3 hydrogens, whereas here carbon is attached to another carbon, here also carbon attached to another carbon. So here carbon attached to 2 hydrogens, 1 carbon, here also carbon attached to 2 hydrogens, 1 carbon. So we cannot find out, we have to move to next. So here it is attached to 1 hydrogen and 2 carbons, because double bond means it is considered as 2 carbons, whereas here it is attached to 1 carbon and 2 hydrogens. So this gets preference. So we can write here this one as first, this one as second. So what do we do here? So what do we do here? We are writing 1, 2 and 3. So it is going clockwise. So it looks like R, but it will be S. So the answer is 1, 2, 3 and 4. So whatever I said I must have written here. You can go slowly. You can pause it and keep reading them. So the answer is 4. So here I had rotated like that, okay. So these both have come left and right. You can do either way, okay. So here when I solved, I looked from this side, but in this how I have solved, I have looked from this side. Either way is perfectly fine, right. So that's it for today. Thank you very much.